Welcome to the second part of Stage 4 on your learning unit, Management of Forms and Spaces. In this video, we will see how to solve oblique triangles using law of sines and law of cosines. First, let's define an oblique triangle. An oblique triangle is the one where none of its interior angles are right angles. For this reason, it's not possible to solve it using the Pythagorean theorem. To solve it, we must use the law of sines or the law of cosines. And when we say to solve it, it means to determine the magnitude of the three interior angles A, B, and C, and the size of sides A, B, and C. So, to solve an oblique triangle, we need to know at least three elements: one side and two angles, two sides and the opposite angle to one of them, two sides and the angle between them, or the three sides. In the first two cases, we apply the law of sines, and in cases 3 and 4, we apply the law of cosines. Let's see first the law of sines. In every triangle, the lengths of their sides are proportional to the sine of their opposite angles. So, we have that in a triangle ABC, side A over sine of angle A equals side B over sine of angle B. And it is also equal to side C over sine of angle C. It means that side B over sine of angle B equals side C over sine of angle C. These relations are known as law of sines. Let's see how to apply this law. First, we'll check case 1, in which one side and two angles are known. From triangle ABC, it is known that side C measures 30 units and that angles A and B measures 85 degrees 40 minutes and 47 degrees 50 minutes respectively. Determine the magnitude of angle C and the measure of sides A and B. To obtain the value of angle C, remember that the sum of the interior angles in a triangle equals 180 degrees. So, the value of C must be obtained subtracting 180 degrees minus the values of angles A and B. That is 180 degrees minus 85 degrees 40 minutes minus 47 degrees 50 minutes. That is equal to 46 degrees 30 minutes. This angle will help us to obtain the values of sides A and B because we are going to relate it with its opposite side with the law of sines. We apply then the law of sines to determine the value of one of the missing sides, for example, side A. The law of sines establishes that side A over sine of angle A equals side C over sine of angle C. We substitute the known values and we have that A over sine of 85 degrees 40 minutes equals 30 over sine of 46 30 minutes. We clear for A and side A equals 30 times sine of 85 degrees 40 minutes over sine of 46 degrees 30 minutes. We perform the operation and we have that side A equals 41.24 units. Now let's continue with side B. And once again, we apply the law of sines. And we have that side B over sine of angle B equals side C over sine of angle C. We substitute the known values and we have that side B over sine of 47 degrees 50 minutes equals 30 over sine of 46 30 minutes. We clear for B and then side B equals 30 times sine of 47 degrees 50 minutes over sine of 46 degrees 30 minutes. We perform the operation and we have that side B equals 30.65 units. Let's see now case 2, where two sides and the opposite angle to one of them are known. Let's consider again a triangle ABC, and that we know sides A and B, and also we know angle A. With this information, we can determine first the value of angle B, and we can use the law of sines. So, side A over sine of angle A equals side B over sine of angle B. Clear sine of angle B, and it is equal to side B multiplying sine of angle A over side A. However, in this case, case 2, there are three possible situations. If sine of angle B is greater than 1, we cannot get the inverse sine of a number greater than 1, so there is no triangle. If sine of angle B equals 1, it means that angle B is a right angle, and the triangle must be solved as we did it in stage 3. And when sine of angle B is less than 1, then one or two triangles can be formed. Considering this, let's see the following example. We have the triangle AHS, and it is known that side A equals 9 units, side H measures 17 units, and angle A measures 57 degrees. So, we have to determine angles H and S and side S. Using the law of sines, we can begin with angle H. Substituting the given values, we have 9 over sine of 57 degrees equals 17 over sine of angle H. We clear sine of H, and it is equal to 17 times sine of 57 degrees over 9. We perform the operation, and we have that sine of angle H is 1.58. Because this value is greater than 1, we cannot get a value for angle H. That means that there's no triangle. Let's see another example. For the triangle BIG, it is known that side B measures 9 units, side G measures 12 units, and angle B is 40 degrees. We need to determine then the magnitude of angles I and G and side I. We use the law of sines to relate the known sides and angle, and we have side B over sine of angle B equals side G over sine of angle G. We substitute the known values, and we have 9 over sine of 40 degrees equals 12 over sine of angle G. We clear for sine of angle G, and it is equal to 12 times sine of 40 degrees over 9. So, sine of angle G equals 0.857. Because the value of sine of angle G is a number less than 1, then one or two triangles are possible. We apply then the inverse sine of 0.857, and angle G equals 58.99 degrees, or 58 degrees, 59 minutes, 24 seconds. And now that we have two angles, we can determine the value of angle I, subtracting angles B and angle G from 180 degrees. We have then that angle I equals 180 degrees minus 40 degrees minus 58 degrees, 59 minutes, 24 seconds. And that equals 81 degrees, 36 seconds. So, the triangle is possible because the sum of the three angles fits on the property that says, and I quote, "The sum of the interior angles of a triangle should add 180 degrees." Now we have to get the value of side I. To do that, we are going to use again the law of sines. So, side B over sine of angle B equals side I over sine of angle I. We substitute the known values and we have 9 over sine of 40 degrees equals side I over sine of 81 degrees 36 seconds. We clear for side I and it equals 9 times sine of 81 degrees 36 seconds over sine of 40 degrees. And side I is then equal to 13.82. This is then a possible triangle. Now, let's go back to the step where sine of angle G equals 0.857. As we saw in the first part of this stage, when the trigonometric function sine is positive, there are two angles that fit on this condition. One angle is located in quadrant 1 and the other angle is located in quadrant 2. The angle that we have just obtained, 58 degrees, 59 minutes, 24 seconds, is the one located in quadrant 1. But for the angle in quadrant 2, we have to subtract 180 degrees minus 58 degrees, 59 minutes, 24 seconds. And the angle is 121 degrees, 36 seconds. So angle I is calculated by 180 degrees minus 40 degrees minus 121 degrees 36 seconds. That is equal to 18 degrees 59 minutes 24 seconds. This value is also possible because it also fits on the property of the sum of the interior angles of a triangle. Then we have another possible triangle, and we have to determine the value of side I for it. We are going to use again the law of sines. So 9 over sine of 40 degrees equals side I over sine of 18 degrees, 59 minutes, 24 seconds. We clear for side I, and that is equal to 9 times sine of 18 degrees, 59 minutes, 24 seconds over sine of 40 degrees. So side I equals 4.55 units. And now our second possible triangle is complete. Let's see now a real context problem where we can apply the law of sines. The problem is, calculate the distance that a worker must travel to go up and down with his wheelbarrow by a ramp if it measures 30 meters of base and has an inclination angle of 25 degrees on the way up and 37 degrees on the way down. We can write the names of angles A, B, and C as a reference. As we have angles A and B, angle C is calculated subtracting angles A and B from 180 degrees. Then C equals 180 degrees minus 25 degrees minus 37 degrees. That is equal to 118 degrees. Now we can relate angles A and C with their opposite sides. So side A over sine of angle A equals side C over sine of angle C. That is, side A over sine of 25 equals 30 over sine of 118 degrees. We clear A and it is equal to 30 times sine of 25 degrees over sine of 118 degrees. So, distance A equals 14.36 meters. We do the same for side B. B over sine of angle B equals C over sine of angle C. So, B over sine of 37 degrees equals 30 over sine of 118 degrees. We clear for side B, that is equal to 30 times sine of 37 degrees over sine of 118 degrees. Then, distance B equals 20.45 meters. Finally, to calculate the total distance that the worker has to travel, we have to add distance A plus distance B. It means add 14.36 plus 20.45 meters. So the total distance is 34.81 meters. Let's continue now with the law of cosines. In every triangle, the square of one side is equal to the sum of the squares of the other two sides minus the double product of these two sides multiplied by the cosine of the opposite angle to the considered side. For example, in triangle ABC, if we choose side A, we have that the square of side A equals B squared plus C squared minus the double product of B times C that multiplies the cosine of angle A, which is opposite to side A. If we choose side B, then we have that B squared equals A squared plus C squared minus the double product of A times C that multiplies the cosine of angle B. And if we choose side C, we have that C squared equals A squared plus B squared minus the double product of A times B that multiplies the cosine of angle C. The law of cosines is used in cases 3 and 4. Let's see an example for case 3, where two sides and the angle between them are known. The triangle that we must solve is triangle ABC, where side A equals 7 units and side C equals 9 units. Also, it is known that angle B is 35 degrees. We have to determine the value of side B and angles A and C. We use then the law of cosines, and because side B is the one that we have to find, then B squared equals A squared plus C squared minus 2 times A times C times cosine of B. Substituting the known values, we have that B squared equals 7 squared plus 9 squared minus 2 times 7 times 9 times cosine of 35 degrees. It is 49 plus 81 minus 103.21. Then B squared equals 26.79. Now we have to get the square root in both sides of the equation. So B equals 5.175 units. Now we have to continue with an angle. Let's begin with angle A. Once again, we use the law of cosines. And because the angle that we need to find is the opposite to side A, we use the formula A squared equals B squared plus C squared minus 2 times B times C times cosine of angle A. That is 7 squared equals 5.175 squared plus 9 squared minus 2 times 5.175 times 9 times cosine of angle A. We clear for cosine of angle A, and it equals 7 squared minus 5.175 squared minus 9 squared, all over minus 2 times 5.175 times 9. We solve it and we have that cosine of angle A equals 0.631. So we get the inverse cosine of 0.631 and angle A equals 50.88 degrees or 50 degrees, 52 minutes, 48 seconds. And finally, angle C must be obtained subtracting 180 degrees minus 50 degrees, 52 minutes, 48 seconds minus 35 degrees. So angle C equals 94 degrees, 7 minutes, 12 seconds. Now let's see an example for case 4, where the three sides are known. We have the triangle ABC, and side A measures 320 units, side B measures 800 units, and side C measures 480 units. We must determine the value of the three interior angles. We could begin with any of its angles. If we choose angle A, we use the law of cosines as a squared equals b squared plus c squared minus 2 times b times c times cosine of angle A. We clear for cosine of A, and it equals a squared minus b squared minus c squared divided by minus 2 times b times c. So, cosine of A equals 320 squared minus 500 squared minus 480 squared. All this over minus 2 times 500 times 480, which is equal to 0.7875. Then we get the inverse cosine of 0.7875, so angle A equals 38.05 degrees or 38 degrees 3 minutes. We use again the law of cosines to get the value of angle B. So b squared equals a squared plus c squared minus 2 times a times c times cosine of angle B. We clear for cosine of B, and it equals b squared minus a squared minus c squared divided by 2 times a times c. Substituting the values we already know, we have that cosine of angle B equals 500 squared minus 320 squared minus 480 squared divided by minus 2 times 320 times 480. So, cosine of B equals 0.2695. We get the inverse cosine of 0.2695, and angle B equals 74.36 degrees or 74 degrees 21 minutes 36 seconds. Once we have the values of angles A and B, angle C must be calculated by 180 minus 38 degrees 3 minutes minus 74 degrees 21 minutes 36 seconds. So angle C equals 67 degrees 35 minutes 24 seconds. Let's see now a real context problem to apply the law of cosines. The problem is, to calculate the width EF of a bay, two distances DE and DF and the angle FDE are measured from a point D. If DE equals 8 kilometers, DF equals 9 kilometers, and angle FDE equals 65 degrees 30 minutes, what is the width of the bay? Here we have a triangle where we need to determine the value of side D, and we already know the measure of sides E and F, and also angle D, which is opposite to the side we have to find. We apply the law of cosines for side D, so D squared equals E squared plus F squared minus 2 times E times F times cosine of angle D. We substitute the known values and we have D squared equals 9 squared plus 8 squared minus 2 times 9 times 8 times cosine of 65 degrees 30 minutes. That is 81 plus 64 minus 59.72. We solve this and D squared equals 85.28. Now we get the square root of 85.28 and D equals 9.23. It means that the width of the bay is 9.23 kilometers. As a last topic, we will see the area of an oblique triangle. We know that the area of a triangle is given by the product of base and height divided by 2. However, if the height is not given, we have another way to get the area using the trigonometric function sine. So, how can we do it? Let's consider triangle ABC. Let's trace the height in this triangle. As you can see, two right triangles are formed. Let's work with the left one. If we want to get the value of h, we will use the sign of angle C, that is h over a, because h is the opposite leg and a is the hypotenuse. From this expression, we can clear height h, that is equal to a times sine of angle C. We substitute this value of h into the formula of area. So area equals b, that is the base, times a times sine of angle C divided by 2. Now let's work with the other triangle. Here we have that sine of angle A equals height h over side C. If we clear height h, it equals C times sine of angle A. Substituting this into the formula of area, we have that area equals base B times C times sine of angle A divided by 2. As you can see, the area can be calculated multiplying two sides by the sine of the angle between them, and this product divided by 2. So, for this triangle, other way to determine the area is side A times side C times sine of angle B divided by 2. So, in a triangle ABC, where sides B and C measure 13 and 15 units respectively, and angle A is 70 degrees, determine the area of that triangle. The area must be calculated multiplying the given sides B and C by the sine of angle A, that is the angle between them, and then divided by 2. It is 13 times 15 times sine of 70 degrees over 2. So the area of this triangle is 91.62 square units. We have finished the content of Stage 4. In this video, we saw the law of sines, the law of cosines, and also how to get the area of an oblique triangle. Don't forget to solve the learning activities on your textbook to practice the content included in this video. See you next time. Bye!